Good morning to everyone. So I will discuss in this class molecular orbital theory. Okay. So in the next two class, I have completed valence bond theory and BSc pair theory. Today, this is molecular orbital theory. This is very important for from exam point of view. For each and every exam, one or two questions are asked in this topic. Okay. So we know that valence bond theory cannot explain the properties of the molecule, but in MOT, that is this will explain the all properties of the molecule. Okay, that is if it is diamagnetic or paramagnetic, that is okay. So if we take an example, that is oxygen O2 molecule, that is in valence bond theory, this is diamagnetic in nature. What is diamagnetic molecule? That is repelled by magnetic field. Okay, but in MOT, that is O2 molecule is paramagnetic. Okay, and so it is attracted by the magnetic field. So basically O2 molecule is either diamagnetic or paramagnetic. It cannot explain by the PVT. So MOT theory is here. Okay. Next, postulates of this theory. Okay, so first is electron in a molecule are represent in molecular orbital as in electron in atoms are present in atomic orbitals, and molecular orbitals are formed by overlapping of atomic orbitals. Number of molecular orbital is equal to number of atomic orbital, and half of the MO have less energy, that is bonding molecular orbital more stable, and half of the molecular orbital having higher in energy. Okay, so anti-bonding molecular orbital, that is less stable. Okay, so basically in this diagram it is easily you can easily understand that basically two atomic orbitals are there, so number of atomic orbitals is equal to 2 MO are there. Okay, so number of atomic orbitals is equal to number of molecular orbitals, and here to show two atomic orbitals are overlapping to each other and two MOs are formed. The number of electrons in atomic orbitals are same in the number of atomic electron in the atomic bonding molecular orbital and antibonding molecular orbital, and here half of the MO, that is bonding molecular orbital, are less in energy, and half of the molecular orbital, that is higher in energy, that is less stable. Okay, next, electrons are filled in MO according to above principle. Okay, which is based on Hund's rule and Pauli exclusion principle. What is this Pauli exclusion principle? That is electron first go to the bonding molecular orbital, that is less energy. Okay, then which have less energy, then electron goes to the higher energy orbital, that is antibonding molecular orbital. Okay, next, here it is a very important formula, that is bond order calculation. Bond order is equal to number of bonding electron minus number of antibonding electron by 2. This is very important formula. Okay, so here I can just gist from this topic that bond order may be positive, negative, 0 or fractional. From this line questions are asked often, and molecule exists if bond order is positive, but molecule does not exist if bond order is negative or 0. Okay, so this is very much important lines. Okay, you have to remember. Next, bond length. Bond length is inversely proportional to bond order. Okay, so if we take an example that if the bond length is this, the bond order is, and if the bond length is this. Okay, so bond length, if bond length is increases, then bond order, that is strength of bond, is decreases. Okay, next, bond energy is proportional to bond order. Okay, so here we can say that triple bond is more stronger, or bond energy is more than single bond. Okay, so bond energy is proportional to bond dissociation energy is proportional to bond order. So here we can say that bond energy of triple bond or bond dissociation energy of triple bond is more than bond energy of the single bond. Okay, next, stability of the molecule is proportional to bond order. Okay, so we can say that for a triple bond molecule it is more stable than a single bond molecule. Okay, next, a molecule is paramagnetic if there is unpaired electron in it. Okay, for molecular orbital, if there is unpaired electron, that is paramagnetic. If all electrons are paired, then diamagnetic. Okay, so diamagnetic molecules are repelled by magnetic field, and paramagnetic molecules are attracted by magnetic field. So basically we can say that molecular orbitals are formed by overlapping of two atomic orbitals, and two MOs are formed, that is, one is bonding molecular orbital, one is anti-bonding molecular orbital. Okay, so now we have a question that why bonding molecular orbital is more stable or less energetic, and anti-bonding molecular orbital is more energetic or less stable? Because electron density is present between two nuclei in bonding molecular orbital. Okay, so hence there is a less repulsion between nuclei of bonding molecular orbital, so energy decreases and stability increases. Okay, but in case of antibonding molecular orbital, electron density is present away from the nucleus, so repulsion between nucleus is increases in antibonding molecular orbital, so stability decreases and energy increases. Now you can see that linear combination of atomic orbitals, LCAO method. Okay, so today I will discuss just linear combination of atomic orbitals, but the conditions are discussed in the next class. Okay, so basically atomic orbitals are SPDF. Okay, these are the atomic orbitals, but molecular orbitals are there two molecular orbitals, that is represented by sigma and pi. If we can say that bonding molecular orbital, that is sigma and pi, and if that is antibonding molecular orbital, that is sigma star and pi star. Okay, so next, how can we form a sigma molecular orbital? Basically two types of sigma molecular orbitals are there, that is SS overlapping and PP overlapping. Okay, so first we can draw SS overlapping. How it is an energy profile? This is a diagram of SS overlapping. Sigma bond is formation, that is energy curve. Okay, basically two atomic orbitals are there, 1s and 1s. Okay, these two atomic orbitals are overlapped and to form one bonding molecular orbital, one anti-bonding molecular orbital. That is first one bonding molecular orbital, that is sigma 1s, and anti-bonding molecular orbital, that is sigma star 1s. Okay, so sigma is basically formed by psi function, psi of A plus psi of B, and sigma star is formed by psi A minus psi B. Now we can this representation, if we given by this example or this type of orbital interaction, that is if two nucleus, that is 1s and 1s is there, if we subtract an addition of these two nuclei, then if this type of formation is takes place, then this is sigma 1s. Okay, if there is a nodal plane or subtraction of these two, okay, we can say that if this is positive and minus this, okay, minus this, so this type of formation is takes place. Okay, so this is a nodal plane and this is sigma star 1s. Okay, now PP overlapping. For PP overlapping, PZ in convention, PZ is forming of a sigma bond, and PX and PY is form that is pi bond. Okay, so this is basically energy diagram. This is 2pz and this is 2pz. Okay, so these 2pz atomic orbitals are combined to each other and two molecular orbitals are formed, that is one is bonding molecular, that is orbital, that is sigma 2pz, and another is anti-bonding molecular orbital, that is sigma star 2pz. Okay, so if we draw this by an orbital diagram, okay, so that is 2pz and 2pz. Okay, if we addition these two orbitals, then two positive parts are attached to each other and this type of orbitals are formed. Okay, this is sigma 2pz, and if we subtract these two parts, then sigma star 2pz is formed. Okay, next pi mo. Okay, it is energy diagram of pi mo. We can earlier says that px and py are formed pi mo. Okay, so basically it is an energy profile diagram. So this is px orbital and this is px orbital. If these two px orbitals are overlapping each other, and one is formed pi 2px, another is formed pi star 2px. Okay, so how can we draw this? Because now see that these are two px orbital. Okay, if we addition these two orbitals, then this type of formation is takes place, and if this is the molecular axis, then this type of formation is takes place. Okay, this is pi 2px, and if there is a nodal plane, subtract these 2px orbital, then subtract if we then here one nodal plane is there, and this is the formation of pi star 2px. Okay, so basically these are the LCAO, linear combination of atomic orbitals. The reasons or conditions I will discuss in the next video. Okay.